Question 13. We are now beyond the halfway point out of 25 questions. A 4-digit integer contains one each of these digits, 3, 4, 5, 6. What is the probability that the number is a multiple of 5? Number theory, probability, and counting. Whenever we talk about a number made with one each of digits, usually this talks about something called permutations. And maybe one of the first things you're thinking about already is in probability, I want to know how many possibilities there are to permute 3, 4, 5, and 6. And indeed, if I want to know the number of numbers with permutation of 3, 4, 5, and 6, this answer is 4 factorial, written this way. 4 factorial, which means 4 times 3 times 2 times 1. Why? As a very brief reminder, why that is because this is a number, and the number has 4 digits. Let's think of the 4 digits like this. If you have 4 digits, and you're trying to see what is going to go in the first place, I have 4 choices. Because in the first place it can be 3 or 4 or 5 or 6. But whatever I put there, the second place has only 3 choices left. Because it has to be not that x that I had put there. And then we just keep going. And the 2 choices left for here, and then 1 choice left for the last one. And since each of these is always, if I've done these first 2, there are always 2 choices left and always 1 choice left, I can multiply these together, and that tells me how many different ways I can make my number. Okay, and this is a probability question. It asks what probability, what is the fraction of them which are divisible by 5? Divisible by 5 is very easy because I just have to end with a 0 or a 5, and there's no 0. So in that case, divisible by 5, I don't have much choice. If I'm asking for how many ways can I make one of these numbers to be divisible by 5, the last one has to be 5. And so the other digits that I have to play with are 3, 4, and 6. Of the other ones, 3, 4, and 6, which are somewhere here, the number of ways I can put them there, for the same reason as before, is 3 factorial, which is 3 ways to decide what goes in the first one, 2 ways to decide what's in the second one, 1 way to decide what's in the third one. So this is 6. The previous one, 4 factorial, was 24. And so the probability that it's divisible by 5 is just 6 divided by 24, which is 1/4. And this would be one way to do the problem. But I want to share another way of doing the problem. The other way of doing the problem is to think backwards, and actually to remember a little bit more deeply why I actually multiply when I do 4 times 3 times 2 times 1. It's nice to know the deep reasons why you do something, not just the formula, because then you can use that power to do more. If I know that I need to end with 5, here's an interesting way that I can think of how to make these 4 times 3 times 2 times 1 numbers. Let's think from the right-hand side. What are these numbers like anyway? These numbers will end with 3 or 4 or 5 or 6. These are the possible last digits. I'm drawing a tree diagram, and I'm going to do the 4 times 3 times 2 times 1 backwards. If I know these are my last digits of the number, well then what could the second last digit of the number be? If the last digit was 3, the second last digit here could be either 4 or 5 or 6. If the last digit was 4, the second last digit could be 3 or 5 or 6. If the last digit was 5, the second last digit could be 3 or 4 or 6. If the last digit was 6, the second last digit could be 3 or 4 or 5. You see, there were 4 ways to do this split, and then there are always 3 ways to do that split. And then we have to keep going, because over here, if I have now a 4 as my second last digit and a 3 as my last digit, the two possibilities for the second digit are 5 or 6. Here I can have 4 or 6, and here I can have 4 or 5. And you can see that all of these trees would expand. For example, this one here, this one would go to either 4 or 5. This one would either go to 3 or 5. This would either go to 3 or 4. But the important thing is all these trees expand in the same way. And in the very, very end, just to make one of them complete for the drawing, here 3, 4, 5, this one there's only one choice to finish. Here I already have a 3, 4, 6, and so this one, the only thing left is 5. Here is a 3, 5, 4, the only thing left is 6. This is a 3, 5, 6, the only thing left is 4. This is a 3, 6, 4, the only thing left is 5. This is a 3, 6, 5, the only thing left is 4. And I'm showing that always these expand. And that's the real reason why you say there are 4 ways that this breaks, and each of these breaks in 3 ways, and then each of those breaks in 2 ways, always. And the last one always has only 1 coming out. But I'm only looking at probabilities. If I care that the last digit is 5, can you see why it's 1/4 chance that the last digit is 5? Yes, because if I'm doing this from the right-hand side out, everything that comes out in this one, this tree, is one of the ones that I want to count. And all of these 4 trees are the same size. And therefore, there's exactly a 1 out of 4 chance that my number is a multiple of 5. This is just showing 2 different ways. One way is to know formulas and to multiply. That works well. Another way is to think about this picture. This one might have looked like the slower way. But I'll actually share that if you know this way, if you know this way of thinking, it's actually the faster way. And you can look at the problem, and you can actually just say, oh, I would go from the right side, and I have a 1 in 4 chance of having a 5. Done. 1/4.